Good day, students. Today, let us look into N-slit Fraunhofer diffraction. Here, diffraction takes place through a number of slits, and hence we call it N-slit Fraunhofer diffraction. We had seen the diffraction pattern due to a single slit, and the pattern could be mathematically represented by the expression for intensity I is equal to I naught sine square alpha by alpha square, where alpha represents the phase of the wave. And it is again mathematically given as 2 alpha is equal to 2 pi by lambda times path difference A sine theta, where theta is the angle of diffraction. The diffraction pattern was observed as such figure shown in the right side. We have a central bright maxima surrounded on either sides by secondary maximas and minimas of gradually decreasing intensities. Now, in the diffraction pattern due to a double slit, the intensity of the pattern was observed to be I is equal to 4 times I naught sine square alpha by alpha square into cos square beta, where alpha represents the phase between the diffracting beams through a single slit and beta represents the phase between the interfering beams between the two slits. And phase difference beta is given as delta by 2, that is equal to 2 pi by 2 lambda into path difference A plus B sine theta, where again theta is the angle of diffraction. On the right side, we can see the intensity distribution of the diffracted light due to double slit. Here, in the central region, in the central bright maximum, a number of interference maximas and minimas have entered. Okay, so here the interference pattern has overlapped the diffraction pattern. Now, in the diffraction pattern due to n number of slits, the intensity observed on the screen can be mathematically represented by the expression I is equal to I naught sine square alpha by alpha square into sine square n beta by sine square beta. Here, sine square alpha by alpha square represents the diffraction effects due to each slit, and sine square n beta by sine square beta represents the interference effects between the secondary waves from each slit. And the phase difference beta is given as delta by 2 is equal to 2 pi by 2 lambda into A plus B sine theta, where theta is the angle of diffraction. On the right side, we can see the diffraction patterns for different number of slits. So on the first pattern where n is equal to 2, we have alternate bright and dark fringes, alternate bright and dark regions having gradually decreasing intensities from the center, right? And when the number of slits is increased to 3, we have certain peaks, sharp peaks. They are called the primary maximas, and in between the primary maximas, they will be the secondary minimas, right? This is secondary minima, and this is another secondary minima. And in between those two secondary minimas, we have the secondary maximas. Okay, likewise, when n is equal to 4, here we have a number of primary maximas, a primary maxima, primary maxima, primary maxima, primary maxima, and all their intensities are gradually decreasing when we move away from the center. Okay, and in between these primary maximas, we have secondary minima point, a minima point, a minima point, and secondary maxima points and maxima points. Okay, as the number of slits increases, the primary maximas become more defined, they become more sharp. Okay, and just see the case where n is equal to 10, the primary maximas are far more greater in intensity than the surrounding secondary maximas. Okay, so we will only be able to see the primary maximas. Now let us discuss the positions of primary maximum, and secondary minimas for the n-slit diffraction pattern. Here, the expression for intensity is given as I is equal to I naught sine square alpha by alpha square into sine square n beta by sine square beta. Let this be the first equation. And the expression for phase beta is equal to delta by 2 is equal to 2 pi by 2 lambda into path difference a plus b sine theta, where theta is the angle of diffraction. Now for the points of principal maxima, it is obtained when beta is an integral multiple of pi. That is, if we give values for the integer m, we have beta is equal to 0, pi, 2 pi, 3 pi, etc. So in that case, what happens is the term sine square n beta by sine square beta in the denominator tends to be 0. So in such a case, we always use the L'Hospital rule and take the limit of this term when beta tends to m pi, right? And the limit that will approximately be equal to capital N square. You can calculate it. So in that case, the intensity becomes I is equal to n square I naught sine square alpha by alpha square. Okay, so these are regions of maximum intensity. Here from the expression of beta we get pi by lambda into a plus b sine theta is equal to m pi. On rearranging we get a plus b sine theta is equal to m lambda. Now the secondary minimas are obtained when n beta is equal to p pi. That is, n beta can have values 0, pi, 2 pi, 3 pi, etc. when p is given the integral values 0, 1, 2, 3, etc. Okay. Now in this case, the denominator sine square n beta will tend to be 0. Okay. And hence the intensity I will be equal to 0. So at these points where n beta is equal to p pi condition is satisfied, we get minimas. Okay. But these conditions are not always valid. These points are not always a minima. Some other cases were seen. When p has values 0, n, 2n, etc., when p is having these values, here beta is also having the value 0, pi, 2 pi, 3 pi, etc. Right? When p is 0, we have beta is equal to 0. Right? And when p is equal to capital N, beta will be equal to pi. When p is equal to 2n, we have beta is equal to 2 pi, right? Now for all these beta values, earlier we had what? We had the principal maxima points. So at all these points, the term sine square n beta by sine square beta will be equal to n square and we get maximas there. Hence, on all the values of n beta is equal to p pi, excluding these values, we will be having minimas. That is written as minima is obtained at n beta is equal to p pi, where p is not equal to mn. Here, from the expression of beta, we get pi by lambda into a plus b sine theta is equal to p by n pi. On rearranging, we can write a plus b sine theta is equal to p by n lambda, where p is an integral value that cannot have the values 0, n, 2n, 3n, etc. Okay. So finally, we get the principal maxima points at a plus b sine theta is equal to m lambda. Giving values for m, we have A plus B sine theta is equal to 0, lambda, 2 lambda, 3 lambda, etc. And the secondary minima points are seen where A plus B sine theta is equal to P by n lambda, where P cannot have values 0, n, 2n, 3n, etc. That is, A plus B sine theta will be equal to lambda by n, the first value, right, for P equal to 1. Then 2 lambda by n, here P equal to 2. Then 3 lambda by n, 4 lambda by n, 5 lambda by n, etc. up till n minus 1 lambda by n. Then the next value will be n, right? For P is equal to n, but P cannot have that value. So we skip that and the next value will be n plus 1 lambda by n. Okay. So here, just observe that in this term here, we would have got n lambda by n, that is lambda, right? A plus B sine theta is equal to lambda point would have been here. Okay. So that point is seen as a maxima here. Okay. So in between these 2 points, path difference is equal to 0, path difference is equal to lambda. In between these 2 points, we have this many minimas. Okay, that means we have n minus 1 secondary minimas. And if there are n minus 1 secondary minimas, we will be having n minus 2 secondary maximas. We can see that in the figure. Here when n is equal to 3, okay, these points are the principal maxima points, right? These are the principal maxima points. And between any consecutive principal maximas, we have n minus 1 secondary minimas. Here n is equal to 3, hence 3 minus 1 is equal to 2 secondary minimas. This is 1 secondary minima, 2 secondary minima. Okay. And we have n minus 2 secondary maximas. That is 3 minus 2, we have 1 secondary maximum. Okay. Now, when n is equal to 4, if these are the principal maxima points, okay, we will have n minus 1 secondary minimas, that is 4 minus 1, 3 secondary minimas, 1, 2, 3, and n minus 2, that is 4 minus 2, that is 2 secondary maximas, 2 secondary maximas. Okay. Again, when n is equal to 5, between any 2 consecutive principal maximas, we have 4 secondary minimas, 1, 2, 3, 4, and 3 secondary maximas, 1, 2, 3. Okay. Now, for the principal maxima, we had the condition A plus B sine theta max is equal to m lambda. Now, I'm giving the suffix max to denote that this is the diffraction angle for a principal maxima. Okay. Now, at the first secondary minima, okay, the first secondary minima next to this principal maxima, let the angle towards that first secondary minima be represented as theta 1 minimum. Okay. So here the path difference will be A plus B sine theta 1 minimum is equal to plus or minus lambda by n. These two expressions are obtained from the earlier derivation. Here the expression for principal maxima is taken and the expression for secondary minimum when P is equal to 1 is taken. Hence, we can write A plus B sine of theta max plus or minus delta theta 1 minimum is equal to m lambda plus or minus lambda by n. Okay. So, in this figure, now if this is the principal maxima that we have selected, so from our point of reference here, it will be at an angle theta max. Okay. And again, we have another angle theta 1 minimum to the first secondary minima near to the principal maxima. Okay. Now, if we take the expression for path difference having both these angles, we get A plus B sine of that angle, that is theta max plus or minus delta theta 1 of minimum, the change in the angle for first secondary minimum, and that is equal to m lambda plus or minus lambda by n. Okay. Now here we do a few mathematical operations. Sine A plus or minus B is expanded as sine A cos B plus cos A sine B, and we get A plus B into sine theta max cos delta theta 1 minimum plus or minus cos theta max sine delta theta 1 minimum is equal to m lambda plus or minus lambda by n. Here delta theta 1 minimum is very small. Okay, the angle to the first secondary minima is very small, and hence cos of that angle will always tend to 1, and sine of that angle will tend to that angle. So substituting that values, we get A plus B into sine theta max plus or minus delta theta 1 minimum into cos theta max. It is equal to m lambda plus or minus lambda by n. Now this implies that from this expression A plus B sine theta max is given as m lambda. Okay, so that can cancel out this m lambda, and hence the remaining term will be A plus B delta theta 1 cos theta max is equal to lambda by n. Thus we can write the angular width delta theta 1 minimum is equal to lambda divided by n A plus B cos theta max. That is, the angular width for each principal maxima is given as lambda divided by n A plus B cos theta max. The angular width is directly proportional to the wavelength and inversely proportional to the number of slits. The slit width A, the distance between the slits B, and the diffracting angle theta. Okay. So in this figure, we have the diffraction pattern for n is equal to 4 number of slits. Okay. And let us see the nature of the peaks here. When the number of slits is increased to 10, the peaks become sharply defined. They become more intense. Hence, we get the conclusion that as the number of slits n increases, the angular width will decrease. And as the number of slits n increases, the intensity of the pattern will increase. Hence, for large value of n, we will get sharply defined peaked diffraction pattern. This is what we observe in the diffraction pattern from a plane grating. That is all for today's session. Thank you.